Hi guys, in my previous class I discussed about magnetic field due to a current carrying element. So in this concept we learned a new knowledge that a current carrying conductor is a source of a magnetic field. So according to Biot-Savart law, so the magnetic field due to a current carrying element at a point is directly proportional to the strength of the current, and the magnetic field at a location is directly proportional to the elemental length dl, and the magnetic field is inversely proportional to the distance of the position where we need to find the measure, and the magnetic field is directly proportional to the sine of the angle theta. So here angle theta is the elemental length angle made with the position vector. So this together we can write that so dB is directly proportional to I dl sine theta upon r square. So remove the proportionality constant, so we can replace a constant upon mu naught upon 4 pi, which is here proportionality constant, times I dl sine theta upon r square. So this gives the magnitude of the magnetic field at a given location. And to find the direction, we depends upon the cross product of the given elemental length and the area vector. So in vector form you can represent that dB bar equal to mu naught upon 4 pi times I dl bar cross r bar upon r cube. So this represents the vector form of the Biot-Savart's law. So today let's try apply this law. Let's try apply to this law to find the magnetic field due to a current carrying loop. So this law we applied to find the magnetic field due to a current carrying conductor. So let's try to find the magnetic field due to a current carrying loop. So this is the task by using Biot-Savart's law. Magnetic field at the center of a circular current carrying loop. Suppose if I draw a loop, so let me draw a loop first. So this is a circular loop of radius small r. So in this loop the current is flowing in this direction. So this is at the center of the loop. Now we need to take a small elemental length. So this is the elemental length dl. So that is the elemental length dl, and which is making with the position vector of r bar. And the current in the loop, which is flowing in the clockwise direction. So this is the direction of current. Now if we can apply the magnetic field direction, so the magnetic field direction at the center, so we can apply the right hand thumb rule. So the direction of the magnetic field which is going inside, so the cross mark represents the magnetic field at the center is going inside. So if you directly apply, since this elemental length is perpendicular to r, since the elemental length d bar is perpendicular to the position vector of the location at the center O, is perpendicular to r bar. Therefore the angle between them theta equal to 90 degrees. If theta equal to 90 degrees, so sine 90 degree value equal to 1, because I need to substitute that in the Biot-Savart's formula. Therefore, according to Biot-Savart's law, dB equal to mu naught upon 4 pi times I dl sine theta by r square. So here sine theta value becomes sine 90 degree and 90 degree value becomes 1. Therefore, I can replace this everything with a simple sine 90 degree. That is the angle between the elemental length dl and the position vector r bar. Now dB will be changes, dB equal to mu naught upon 4 pi times I dl upon r square. So this is the small amount of the magnetic field at that particular point. To calculate the total magnetic field, due to entire loop, the total magnetic field due to entire loop is, so here we need to do integration. So integral dB, which gives the total magnetic field B, which gives integral mu naught upon 4 pi times I dl upon r square. So do the integration, B equal to, so here mu naught upon 4 pi times I by r square is the non-integrable terms. So integral of dl. Since it is circular loop, if you take small elemental length as dl, to take the total integration, so total integral dl, the total integral dl value gives that the circumference of the loop. The loop is having radius r, the total circumference value becomes 2 pi r. So the total circumference here, the value will be becomes integral dl equal to 2 pi r. Therefore, magnetic field B equal to mu naught upon 4 pi times I upon r square times 2 pi r. So integral dl value here equal to 2 pi r. Now we can cut the like terms. 2 in 4 and 1 pi gets cancelled and 1 r gets cancelled. We can end up that magnetic field B equal to mu naught upon 2 r times I. So this is the magnetic field due to the entire circular loop. So B equal to mu naught I by 2 pi r. So if you can closely observe this, the magnetic field due to a circular loop is purely depend on the radius of the loop. Here B is directly proportional to the amount of the current and the B is directly proportional to, inversely proportional to radius. So if the current is more in the loop, the amount of the magnetic field is also increases, and if the radius is less, then the amount of the magnetic field is also increases. So here to find the direction, so the direction, to find the direction at the center, so we use the right hand corkscrew rule. So rotate the dl vector on the r vector, so theta, so that here it is clearly visible. So we need to rotate the dl vector over the r vector. So if you place a screw at dB and rotate the dl vector over the r vector, so in the clockwise direction. Now in which direction the screw advances, so that is the direction of the magnetic field. So in this case, the screw is advances inside the paper. So if it is advances inside the paper, so the vector is going inside, the tail part is only visible, so that is represented with the cross mark. So this is how we need to find the direction and magnitude of a given conducting loop, the magnetic field due to at the center of the loop. So B equal to mu naught I by 2 pi r. Now suppose if we change the situation, the situation is like this. Find the magnetic field along the axis of a circular loop. Circular loop axis. Find the magnetic field along the axis of a circular loop. So this is not the simple case as we discussed in the earlier. So first we need to draw a diagram. So let me draw a diagram at here. Consider a loop. So this is a loop. Yeah. So in this loop we need to take axis. Suppose if I draw an axis from the center, so this is the axis of the loop. Now this axis, suppose if I take a point at here, so at this point I would like to find the magnetic field due to this circular loop. So as per we were taking, so let this current is flowing in this direction, maybe counterclockwise direction, yeah, any direction you can take. So we need to consider an elemental length. So let me consider this is a small elemental length dl. So dl is a small elemental length. So this small elemental length is at a distance of the vector at here. Now before that let me take some other so that I can end up with the letters. So first I need to take the what is the radius of the loop. Suppose if I draw a line from the center, yeah, this is the radius of the loop. So the radius of the loop you can take a little a, small a. And the position where we need to find the location P is at a distance of r, position vector r. Now if I draw from the elemental length a line, so this is the point where it is touching. And if you can see clearly, the same one more elemental length across at here, so that is also affects the magnetic field at the same location, since the point is now along in the axis. Now from this point also it is along in the same direction. Now the parameters all the same, so here this elemental length equal to dl. Now at same point P, the magnetic field due to simultaneous two small elemental length dl, they are acting, and the magnetic field is a vector. Now the position vector at here is resolved into two components. Suppose this vector is acting along in this direction. So if I draw this vector acting along in this direction, now this vector is resolved into two components. So one is horizontal component and one is vertical component. And the horizontal component and vertical component, if I mention, so this is one of the vertical component which acts exactly at that point vertically. So that is one of the component of that vector, and one more component which acts along in the same direction. Now this we can represent as point Q, and this is making an angle of pi. So if this angle is pi, and the same angle also, this angle also will be equal, this is also pi. So this component will becomes dB, this is pi, it means it's cos pi, and this component becomes dB sin pi. So that is one of the component. And if you can take one more component, so that is for this elemental length vector. So this is a vector. So this vector, if I mention that this is as a q dash. So the same vector from right now at here is dB bar, is magnetic field. So here also it is dB bar. Now this vector also resolves into two components. So one is horizontal component and one is vertical component. So the vertical component will be resolved at here, and one more horizontal component is resolved at here in the same direction. And this is also makes an angle of pi. Both are same angles because they are coming from at the same point of the elemental length dl. So this is also happens pi. Now this will becomes dB cos pi, and here one more component comes, that becomes dB sin pi. Okay, I hope you can able to analyze this vector resolution. Now all what we need to do, we need to apply that Biot-Savart's law at point P to find the resultant magnetic field. Suppose the distance from, if we take this is as O to P, if I consider this as S is a vector, OP distance is a vector, the same distance also will be from at here. Now if I mention it here, A is radius, A equal to radius, and S is the position vector of point P, position vector of point P relative to the element. Relative to the elemental length. Elemental length dl bar. So these quantities we require to write the Biot-Savart's notation. So according to Biot-Savart's law, the magnetic field at point P due to current carrying element. So according to Biot-Savart law, the magnetic field at P due to elemental length dl, so which we can represent that dB equal to mu naught upon 4 pi times I dl sin theta upon s square. So here s is the position vector, not r. So here S is the position vector. Now if you consider the elemental length dl and position vector are almost perpendicular at here. So the position vector and the elemental length dl, which right at the top where I am highlighting with yellow color, so they both are perpendicular. So the sign value will becomes 1. Since S is perpendicular to dl, therefore theta equal to 90 degree. So sin 90 degrees value becomes 1. Therefore the dB equal to mu naught upon 4 pi times idl upon s square. Now if you can see, the field dB bar lies in the plane of paper which is perpendicular to S bar. Now we need to find the dB bar. Now at the point P, the dB bar is resolved into the components. The vertical components, that is dB cos pi, they both are equal and opposite in direction. These two components, yeah, they both are equal and opposite, they both cancel out each other. But the horizontal components, two components is there, dB sin pi and one more dB sin pi. So they both gets add up because they both are acting in the same direction. So the dB is resolved into two components. dB is resolved into two components. One is dB sin pi, it is along the axis, and another one is dB cos pi, that is perpendicular to the axis. So for any two diagrammatically opposite elements of the loop, so here dB cos pi and dB cos pi, they both are opposite. So they both are equal in quantity and opposite in direction. They both gets cancelled. The components perpendicular to the axis of the loop will be equal and opposite and will cancel out. So the components perpendicular to the axis of the loop will be equal and opposite, and it will cancel and will cancel each other. And the components which is along the same direction, so their axial components, will be add up, will be in the same direction and add up. So here the axial components we need to add and the vertical components we need to cancel out. Therefore finally if you can write, therefore the total magnetic field at point P which is in the direction of C to P, which in the direction of C2P is given by, so B equal to integral of dB sine pi. So from figure we need to calculate what is dB sine pi. So from figure, right triangle, suppose here I supposed to take C as center. From right triangle COP, from right triangle CPO. So from this triangle you can find out what is the, this is S and this is R. What is the value of sine pi? So from right triangle, this is OCP, so this is 90 degree, and this is R, and this is S, this is A. So if you can write the pi, so sine pi equal to, from figure sine pi equal to perpendicular by hypotenuse A upon S. Therefore if you can write B equal to integral dB times A upon S, and we know the dB value from the above equation. dB equal to mu naught upon 4 pi times I dl by S square. So here it is I dl upon S square. Therefore if you can substitute this value at here, now the magnetic field B equal to integral mu naught upon 4 pi times I dl upon S square times A upon S. Yeah, let's simplify further. Therefore magnetic field B equal to, now if you take it out, which are the non-integrable terms at here? So mu naught upon 4 pi times I A upon S cube. It is, everything is non-integrable term, therefore integral of the dl. So this is again a circular loop. The integral of dl equal to the circumference of the loop, which equal to 2 pi A. Therefore B equal to mu naught upon 4 pi times I A upon S cube upon 2 pi A. So 2 pi A, how did I get? Since we consider a loop of radius A, so this is having a radius A. So if it is having a radius A, what is the circumference? The total length dl equal to 2 pi A. So that value here I substituted. Now finally I rewrite that B equal to mu naught, so pi gets cancelled and 2 in 4 2 times, so I can end up mu naught upon 2 S cube times I A square. So this is the final expression. Now from figure, if you can convert the S into known terms, so you can take the sum from the same right triangle. So from right triangle at here, S R A, you can write that S value, S equal to square root of A square plus R square. Since it's 90 degrees, you can apply the Pythagoras theorem. So you can plug in the S value at here. B equal to mu naught I A square upon 2 times A square plus R square whole power 3 by 2. So this is the final expression for the magnetic field along the axial point, the magnitude of the magnetic field along the axial point. So this formula contains all the known terms. So here A is the radius of the loop and R is the position vector of the point where we need to find the magnetic field, and I is the amount of current and mu naught is the permeability. Suppose if that coil, suppose the coil is having n number of turns, coil having capital N turns. What does it mean? Suppose a loop which is made up of a single turn, so it is having only number of turns, it means number of loops is only 1. So in this case n equal to 1. So not only that, if I made one more loop again with the same diameter and with the same radius, so this is the second loop. So likely if I can take one more of the same loop and I can combine, so now it is having n equal to 3. Now like that, if we can increase the number of loops, so we can increase the number of loops, now n equal to 4. Now here in this case how many loops are there? The number of loops here n equal to 4. So number of loops means nothing but the number of turns. So here the magnetic field is also depends upon the number of turns. So we can change and write the expression. If the coil is having capital N number of turns, so each turn contributes the magnetic field. So the magnetic field B equal to, this formula will be changes, mu naught times capital N, which is the number of turns, and I times A square upon 2 times A square plus R square whole power 3 by 2. So this is the formula if that coil is having capital N number of turns. So let us try to find or recheck a case. The case is, what is the magnetic field at the center? At the center of the loop. At the center of the loop we already derived. So I derived that B is equal to mu naught IA by 2 pi. So that is the magnetic field due to mu naught I by 2R. So this is the magnetic field due to at the center, mu naught I by 2R. Now at the center of loop, it means the position R we need to consider equal to 0. We are taking that at the center of the loop R equal to 0. But in this formula R I have considered as radius, so if I change that, it will be turns as 2 pi A. So at the center of the loop, it means the distance from the loop to point distance. So this is the loop and this is the R. So here the point we consider. So this R value equal to 0, then only we can able to measure the magnetic field at the center. When R equal to 0 in the above formula, how it will changes? B equal to mu naught N I A square upon 2 times A square. In the place of R we can substitute 0, that value becomes 0 itself. So A square whole power 3 by 2. So this square gets cancelled and B equal to mu naught N I A square upon 2A cube. Again we cancel that A square in A cube. So the final expressions we can leave that B equal to mu naught N I upon 2A. So here N is the number of turns. If number of turns equal to 1, so we are exactly matches what we calculated in the early case. B equal to mu naught I by 2A if N equal to 1, number of turns equal to 1. So this is the expression of a magnetic loop which is having n number of turns, the magnetic field due to at the center, magnetic field due to a current carrying coil at the center. And take one more case. Suppose if the point, the axial point R is far away from the coil, far away from the coil. If it is far away from the coil, we can consider small r is very much greater than A. So in this case, neglect A factor in the above expression. So we will rewrite that expression if we neglecting that. So B equal to mu naught n I A square upon 2 times A square plus R square whole power 3/2. So in this formula, if we neglect A square in denominator, neglect A square in denominator, so the formula will be changes as B equal to mu naught n I A square upon 2 times R square whole power 3/2. Now again you can cut the R square and R cube, so this will be turns as mu naught n I A square upon 2 times R cube, 2 times R cube. Now if you try to change the expression, so it means, suppose if you write the area, so area of a circle that we equal to 2 pi r. So here r is radius, so I can write the 2 pi a. Therefore in the place of a, if we can write that a equal to a upon 2 pi. No need, just let it be like this. Later we can convert when the formula which is needed. So we can end up that B equal to mu naught ni upon 2 r cube. Or if you can write that in terms of area, B equal to mu naught n I A. Here A is the area of the coil upon 2 pi r cube. So here r is the position where we need to find the magnetic field, and here capital N is the number of turns and I is the amount of the current. So this is the field is directed along the axis of the loop, and that is falls. The field is falling around 1 over r cube. If you draw a plot versus magnetic field and the position r, so this is a graph of 1 over r cube. So that's the one I want to represent at here. Now what about the direction? So to find out the direction of this magnetic field, so this is the direction of a magnetic field around a coil. So to find out the direction, we are defining 2 rules. One we call as right hand rule. According to right hand thumb rule, so if you hold the current carrying conductor in this way, so the direction of thumb is represents the direction of current in the current carrying wire. So the curl of the palm of your right hand around the circular wire. So here the curl of the fingers. So this curl of the fingers of your right hand around the circular wire with the fingers pointing the direction of the curl. So the right hand thumb rule gives the direction of the magnetic field. So if you can represent that as a right hand thumb rule, so the curl of fingers is representing the direction of current, and the thumb will represent the direction of the magnetic field in the around the coil. So with the help of right hand thumb rule, we will try to find the direction of the magnetic field. Now for that, so take your right hand, curl the palm of your right hand around the circular wire, just the hold it. How here the diagram is represent the hold it. Now the fingers pointing in the direction of current, and the thumb represents the direction of the magnetic field. So if this is circular coil, and if my fingers, suppose if I fold, so these are my fingers, so these are the fingers are representing the direction of current, and the thumb, so this thumb of my hand is represents the direction of the magnetic field. So now in this case the magnetic field direction is along in this direction. So this is magnetic field direction, and the curl of the fingers represents direction, the direction of the current. So this is a very useful law to find the direction of the magnetic field in the current carrying loop, so which is known as right hand thumb rule. So finally, the magnitude and direction of a current carrying coil along its axial position. So B equal to mu naught n I a square upon 2 times a square plus r square whole power 3 by 2. So here A is the radius and n is the number of turns, and I is the amount of the current which is passing through the loop, and R is the position where we need to find the magnetic field, and mu naught is the permeability.